Hello, my name's Gareth Ellis. I'm going to be talking to you about Node community benchmarking efforts. So a little bit of information about me first. I've been working as a runtime performance analyst at IBM since 2012. Originally, I was looking at the performance of our version of Java that we produce for our stack products. But for the past 18 months, I've been looking at the performance of Node.js. I'm also a member of the benchmarking workgroup. So what we're going to talk about today then, we're going to start off with an introduction to benchmarking and performance testing. We're going to have a look at some ways that we can narrow down regressions that you may come across in Node.js, and then finally talk about the work that we've been doing in the benchmarking workgroup. So, an introduction to benchmarking. Right, okay, fine. Hopefully everyone can hear me still. So an introduction to benchmarking then. The first thing to mention is that benchmarking or performance testing is quite different to, say, functional testing or system testing. In functional testing, typically there's going to be one answer, either it worked, well, there's going to be two answers, either it worked or it didn't. In performance testing, the number of results you could get is pretty much infinite. If you're measuring startup time, it could be anything from 0 milliseconds up to hundreds or thousands of milliseconds. So one of the things that's important to try and do is to change one thing and one thing only between the runs. And the thing that you're going to change is going to typically be whatever it is you're wanting to test. So if you're wanting to see or measure the performance of the latest version of your application code, you'd be trying to keep everything else that's involved the same. So you'd be trying to run it both on the same version of Node.js, running on the same machines, using the same versions of various NPM modules that your project may require. That means that once you've done your tests and you've got a result, you can be fairly confident that the improvement or regression has come from your application code or whatever it is you've changed. Sometimes it can be quite tempting when you go and issue a new version of your application code to also pull in the latest version of all your modules and then upgrade the version of Node that you're running on and maybe also put it on the latest hardware that you've got available. But if you do that, it's going to be very difficult to try and work out where an improvement or a regression has come from. So some of the key challenges that you may face in performance testing. The first one is there is going to be variability in the scores that you get. If you run the same test, say 10 times, there's a very good chance that you'll end up with 10 different answers. So one of the things that you need to get used to is the fact that you can't just simply do a single run and expect to be able to say how good or bad a change was. So one of the things you need to look out for also is false positives. So if you've just checked in a version of your code and you think this is probably going to offer me about a 10% improvement, if you go and do one run and it's about 10% better, then you could be tempted to just stop there and deploy your code. However, it's very important to make sure you collect a large number of results, so making sure that you collect enough results so you're able to be sure about the range of scores that your test or your product may be able to give you. And you're going to then need to document this expected variance so that you can make sure you run the correct number of tests when you actually go through and complete your performance testing. Another key challenge is being able to keep a consistent environment. One of the things that we do to try and make sure that we're always running with the machine in the same state is before we start a round of benchmark testing, we'll go and reboot the machine. Whilst this can sometimes add a little bit of variability to the scores, it means that if we need to go and try and recreate the environment, it's very easy for us to do just by rebooting the machine, rather than having a machine that's been running for months and months and months with thousands of hours of testing done on it. It's going to be very difficult for you to get it back into that same state if, for example, a security update comes along that you need to reboot the machine or have a power cut, something along those sort of lines. Another thing to do trying to keep a consistent environment is being able to isolate the machine. So this includes making sure that people aren't going to be logging in and using the machine whilst you're doing your testing, because otherwise you could actually be measuring the fact that they've been using some of the CPU resource or memory or whatever. Also, if your test is going to be using a network, having a private or a dedicated network available for your test is also a good approach. Now, obviously, the numbers that you may be using for this to try and decide if you've had an improvement or a regression between two versions of either Node or your application code, you're not going to be using these numbers to then go and publish them and say, look how fast our thing can do. Otherwise, in that sort of situation, having a private dedicated network where you've effectively got infinite bandwidth may not be the best way to go. Something else that you can do to try and reduce the variability and also try and make your runs a little bit more consistent would be interleaving the measurements that you take. So say if you've decided that because of the range of scores you get, you're going to need to run your test 10 times, what we may do is we may run our baseline, so basically our known good version once, and then we'll run the version of the code that we want to test, and then the good version again, and the one that we're wanting to test, and so on, and keep switching between these. This would mean that if there is any sort of natural variation in the performance of your machine that you're running on, that should hopefully be taken account by the fact that you keep running one and then the other. The third key challenge to try and get over is jumping to conclusions. It's very easy to see the first run of your baseline and then your build, see a 10% improvement and decide, actually, no, I don't need to bother doing any loads of reruns or anything. I'm happy with that. You need to make sure that you continue with the number of iterations that you've decided is necessary. Sometimes the data can be very misleading, and it's always important to try and get a good set of consistent, reliable data. So two different approaches that you could take to performance testing. The first one would be running micro benchmarks. These are quite useful for being able to measure a specific function or API. For example, you could be measuring how creating a new buffer how long that may take. It's quite good for being able to compare key characteristics of either your application or of a runtime. There are some disadvantages as well, however. One of them being that micro benchmarks may not always represent a real-world improvement. So if you find a micro benchmark and go and check in some changes to try and improve that micro benchmark, it may not actually translate into a real-world improvement in a final product. The second disadvantage of micro benchmarks is that sometimes you risk not actually measuring what you think you're measuring. So one of the ways that quite a lot of micro benchmarks work is by repeating the same action many times. If the JIT or the optimizing JIT that's in your runtime is able to spot that, sometimes they can optimize away the bit that you think you're actually testing. There's quite a lot of information and some interesting videos online as well on this sort of topic about micro benchmarks. The second approach would be a whole system benchmark. So this would be where you'd be trying to test something that represents a solution that may be deployed in production. One of the benchmarks that we use in the benchmarking workgroup is Acme Air, which simulates a fictional airline company. And we measure the throughput or the number of requests a second by users logging in, booking on flights, checking in, logging out, things like that. One of the disadvantages of this type of system, however, is that typically the more things that your system is doing, there's more room to introduce variance in the scores that you're getting out. So whilst you may get more reliable data from a micro benchmark, you could perhaps argue that you may get more useful or real-world data from a whole system benchmark. So if you followed all of these and then you think you've found a regression, what should you do now? The first thing to do is to check that the environment and the data that you've collected is correct. Otherwise, you could find you go and invest many hours of time going down trying to find what the problem was when actually it was just perhaps some variable data that you'd collected. If you're sure and you've had a look at the data and it's within the expected variance that you've measured, what you need to do is have a look at what it is that you changed. If it was you've just upgraded from one version of Node to the other, then you could start having a look at what's changed between those two versions of Node in GitHub. Perhaps use Git bisect to go and narrow down the changes and try and get something that demonstrates the issue that you're seeing. If it's your application, again, if you've got everything in source control, you can perhaps go through and binary chop the different changes that have gone into your new version. It could even be that your environment, you may have found that you've upgraded to a new version of hardware, which now is showing a regression that wasn't previously seen. And that's where you may have to then start looking into perhaps how the JavaScript engine is behaving on the new hardware. It could be that maybe there's something that's not quite working properly. So there's a number of tools that we could use, and as I mentioned earlier as well, you can also use a binary search, so either doing that manually or using something automated like the git bisect function. So if we're running in Node.js, there's a number of different possible sources that a regression may come from. It could be perhaps from some of the native JavaScript libraries. It could be that your new version of Node.js you're testing on has picked up a V8 upgrade, so it could potentially be an issue as a result of a V8 upgrade. It could be that there's been a security fix in OpenSSL, and that's where the regression has come in. Could be libuv update. It could even be that you've gone and downloaded the latest version of your NPM modules, and they've then perhaps caused a regression. Or it could be, if you've updated your version of V8, that now your NPM modules have to be recompiled, and some of the issues have come in that way. There's a few tools that you can also use to have a look at what's happening under the covers. So there's some JavaScript profilers that you can look at. There's one built into Node that we'll have a look at in a second. There's also some extra add-on modules, for example, Appmetrics by IBM that you could use. The other type of tool you could try and make use of would be a native profiler, so something like perf, tprof, oprofile, and these would be looking not only at the resources that your application is using, but also perhaps the resources that some external libraries may be contributing towards the system usage. So a quick example then. So this is a micro benchmark that we've been running at IBM, and it's simply measuring how long it takes to create a new instance of a buffer from an array of numbers. So we have a function there which goes and repeats this 300,000 times. And then it goes and pushes that through a test harness, which the test harness runs it until either we've reached the maximum number of attempts or until we've got some reliable data. When we were running this a few months ago between Node 4.3.2 and Node 4.4, we noticed quite a sizable regression between the two versions. So we can see there that in Node 4.3.2, we were getting about 10 operations a second, 10.6 operations a second. When we went up to Node 4.4, we were only getting just over 6 operations a second. So it's a fairly sizable regression. Again, it may not be something that you would pick up in a larger benchmark, but it's something that we could easily recreate. We could run a number of tests, and we would be fairly confident we could recreate it because they're quite distinct numbers, 6 and 10. So as I mentioned before, Appmetrics could be one option. It's something that you can install through NPM, and you can programmatically get information out about your CPU usage, GC, memory, V8 profiling, loads of different stuff. So you can either write some code that can output that to a file, or you can actually connect it over the network to IBM Health Center to get live monitoring. So the V8 profiler, this comes as part of the Node binary in more recent versions, and you can turn it on by just adding --prof to your command line. This will then generate a file that's called isolate, then a hex number -v8.log, which you can then post-process by doing node --prof process, and then the isolate file that it's created. And that will give you a breakdown of where time is used in various JavaScript methods and other things that V8 is doing. There is also some helper modules that, if you prefer, you can use to try and automate this. So when I went and ran this on our 2 versions of Node, I collected my post-process data, and then I diffed them. So the top few lines is from Node 4.3.2. So we can see 23% spent in lazy compile of the from object in buffer. And then in Node 4.4.0, that had gone up to 47%. So that's perhaps somewhere to look. For completeness, I then also ran it through perf, which is a system profiler that you can get on Linux-based systems. So again, there's a wide number of different options you can pass into perf. These ones that I've got on the screen here I found worked quite well. And again, you can then do perf report to do the post-processing, which then when we compare them, we can see an increase in the time spent from 23% up to 46%. If we weren't able to spot anything in doing that, the next thing that we could have a go at doing would be to binary chop. So we could either do it manually, get a list of the good and bad all the change sets between the good and the bad version, and then go through and manually rebuild them, or we can use git bisect and put together a small script that was able to run our benchmark and then decide if it passed or failed. So a bit of time later, and an issue that we opened in the community, it turned out that this regression was actually due to a change that had been made in the buffer API. So we'd gone through and changed all the declarations for the stepper variables in for loops from var to let, which then triggered an issue that V8 had in its optimizer, where it preferred things to be declared as var instead of let, and that's going to carry on to be the case until turbofan becomes the default optimizer. Again, you can have a look at a bit more information about it if you wish in that pull request 5819. So now I'm going to briefly talk about the work that we've been doing in the community benchmark work group, some of the things that we're up to and how you could also get involved. So the work group has a mandate to track and evangelize performance gains between different node releases. Some of our goals are to define use cases, identify benchmarks that we can run, and then run and capture the results. We've got 12 members at the moment. We have meetings every month or so, with the next meeting likely to happen in probably next week. So you can get some more information by looking on GitHub at Node.js benchmarking. You can also look at the graphs and charts from the results of our runs at benchmarking.nodejs.org. So this is a list of the people that we've currently got involved. Michael Dawson from IBM is the facilitator, along with some people from various other communities and also freelancers. Some of the benchmarks that we're currently running, so we've got some that measure startup time. So that's looking at how long it takes for a node to actually start and get going. We've got some that are measuring the footprint, so how much memory node actually uses whilst it's running, the amount of time it takes to require a module, and with most projects using a large number of NPM modules, both as direct requirements and then child requirements, that's a very important metric. We run Acme Air, as I mentioned before, where we track the throughput, or the number of operations a second. We track the response time, and also we take footprint measurements at different stages of the run to see how Node performs, not only when it's idle, but also when it's just done a lot of work. We also have a Docker file available for comparing two different versions of Node. So if you want to have a look at how two different versions of Node compare, you can run those through the Docker file, and it will produce some output at the end where it will tell you if the new version is better or worse. We're also in the process of putting together the facility to allow to test particular pull requests against some of the benchmarks that come as part of the node source, which that's taking place in 8157. So on benchmarking.nodejs.org, we have a number of charts that look a bit like this. So this is the one where we're tracking throughput on Acme Air. You can hopefully see there's a bit of a jump around April time. So that was when we took a new version of V8. You'll also notice that more recently, mid-August, we've got a blue line at the bottom. That was where a change that was going into master actually broke the MongoDB module that Acme Air was using. So we had to update our version to a newer version of the MongoDB module, which as a result actually caused a slight performance regression compared to the previous sets of data that we've collected, which is why that we see the drop-off on most of the lines towards the end of August. Some of the use cases that we've identified here then. So one of the first use case that we've identified is back-end API services. So this is going to be typically scenarios that are using REST or REST-like calls, mostly over HTTP and public infrastructure. Second one would be service-oriented architectures. So this is typically where APIs are provided that may go and call into a large number of other APIs to produce one result. Generating and serving, microservice-based applications. So these are going to typically be very nimble, low-resource, quick startup applications, where there may also be a number of different microservices running on the same system. So a small amount of footprint there would be better. Generating and serving dynamic web page content. So this is looking at modules such as Express, Happy, Coa, React, and so on. Single page applications, where you'll be loading a page once, and then further communication to the back end will happen via WebSockets or HTTP2. Agents and data collectors. So this is where people are going to be deploying instances of Node onto their network to monitor certain things, and they're going to want the ability not only for it to be able to report back, but to be able to push out new versions and then the instance restart itself. And then also small scripts just for doing little bits of tooling. So rather than writing things in Bash or Python, some people are now starting to run more things in Node, where they want it to start up very quickly, not use very much resource, and then once it's done, go away very quickly as well. Some of the key attributes, so these are different metrics that we're looking to track, and obviously we've still got some gaps here that we need to fill in. So we've got 2 memory footprint measures, one just how much Node uses once it's started before it's done any work, and then one also after load. The Node CPU usage at idle, ideally that shouldn't really be using any CPU at all. Throughput, as we're tracking through Acme operations per second, and then how large the Node package is when you download it, and then also once you've installed it, how much space is it going to be using on disk. We also want to start collecting some metrics on GC, not only the CPU usage impact on Node, but also how quickly it's able to allocate memory, tracking the max pause times when under load. Finally then, if you're wanting to get involved, you can take a look at the GitHub repo, Node.js benchmarking, have a look at what's there, have a look around at the charts. If you think something's missing or if you think something's wrong, then by all means open an issue. We've got an issue open at the moment, organising the next meeting, so if you wish, you can either join the meeting and contribute or even just listen in via the YouTube on the air recording. And that is it. Thank you very much.